All right, well, hello friends. How we all doing here? So we are going to share our screen here today. It's been a while since we've been out here making videos about pre-calculus and whatnot. And so Miss Love and I, we were kind of looking at things. We noticed that there are some things from algebra 2 / integrated 3 that maybe we just need a little bit of extra help on. So before you guys head to calculus, we're going to go back and take a look at more of an algebra type idea, and that's this idea of property of exponents. So this first thing we're going to look at here, friends, is just reviewing some of our rules. Remember that when you're multiplying numbers with the same base, you add the exponents. All of this is built up off the idea of same base. So when we're multiplying numbers with the same base, add the exponents. And when you're dividing numbers with the same base, you subtract the exponents. Okay. Then we also looked at if we have anytime we have an exponent raised to an exponent, it's like distributing. So we're going to take that exponent inside and we're going to multiply it by the exponents outside. And we'll see all this here in a second. If we have a negative exponent, we are going to flip it and flip it good. So imagine that it's over 1. So to get rid of the negative, we're going to move it to the bottom and make it positive. Likewise, if we have a negative exponent in the bottom, we're going to move it to the top and it's going to become a positive exponent. Same idea. It's just if you have a negative exponent, you can flip it to the other side of the fraction bar and go ahead and make it positive. Anything to the 0 power is 1 except for 0. That's called indeterminate. And anytime we have a radical, we can change a radical to be an exponent. So the numerator or the exponent becomes the numerator. And the root, whatever that index is of a radical, becomes the denominator. So we're going to see a lot of these things here as we go through and just do a quick little run through, just remembering how to deal with all our exponent stuff as we go through and try some different properties. So we're just going to play with a few and then we'll just see where we're at here. So simplifying, first up, x to the 12th times x to the -4 all over x to the -3. So there's a bunch of ways we could look at this. I usually like to just deal with combining everything on top first and combining everything on the bottom first. You don't have to. You can do other things. You could actually take all the negatives and flip-flop them if you wanted to. It's really pretty much up to you. But I like to go ahead and do that. So if I'm multiplying numbers with the same exponents, I'm going to add, or same base, I'm going to add their exponents. So 12 and -4, that would be 8. Friends, you know that I'm going to every once in a while make little word mistakes. So I'm sure you can chuckle along with me. We've been going through pre-cal together all year long. I'm sure by now you've got this all figured out. And then the last thing there, friends, if we're dividing numbers with the same base, we're going to subtract our exponents. So 8 minus a -3 would be 11. So nothing too terribly horrible. We just want to make sure we add exponents when we're multiplying, subtract exponents when we are dividing. Now, notice this one here is just got a little bit more of a problem to it because you have this addition in the middle. Now, because we have that addition in the middle, we can't combine any exponents right from the very beginning. We have to kind of play with it a little bit. So there's a bunch of different ways you could do it. You could go ahead and turn all these into fractions and then do a complex fraction if you wanted to. So what I mean by that is if you wanted to, you could take this problem right here and you can make it x to the 7th plus 1 over x cubed. And then make this 1 over x to the 5th. And then multiply by the greatest common factor, which isn't a bad way to do it. All right. If you did it that way, you would have x to the 5th, since that is the biggest exponent in the denominator. You'd multiply everything by x to the 5th. And you'd end up with something kind of like this. That's not the color we wanted. There we go. you'd end up with 5 plus 7, that'd be x to the 12th. X to the 5th over x to the 3rd. And the denominator, you would have 1, which would lead you to x to the 12th plus x squared. And that'd be totally okay to do it that way. And one of the things I like about these guys is there really is no rhyme or reason. As long as you're following the rules, it's kind of whatever you see. Like, for instance, when I look at this problem, one of the things I see is I could have just taken this whole thing, done this to it. And I could have brought that x to the negative 5th up to the top, made it a positive. And from there, if I wanted to, I could go through and distribute it. When you're multiplying numbers with the same base, you just add their exponents. So we end up with x to the 12th, same thing, plus x squared. And again, one of the things I love about exponents and logs is it's kind of like verifying our trig identities. It's really whatever you see. All right, you get to have fun with it. If you see something, go with it. It's not wrong, so don't worry about it. On this next one, if you take a look at it here, now, if we're missing exponents, we always got to make sure we add a 1 in there. So anytime you're missing an exponent, add a 1. And then what we're going to do with this is we're going to take it and we are going to distribute it, just like we did on that last one with the x to the 5th, distribute it into the parentheses. The entire time making sure that we multiply numbers with the same base. So x to the 1st times x to the 1st, that would be x to the 2nd. Y to the negative 2, y squared, that would be y to the 0. And then over here, we have our x and negative 3, so there's nothing to combine there. We'll just go ahead and leave that alone. But then we have our y's here. So y to the negative 2nd, and we have y cubed. So multiply numbers with the same base, add their exponents, which would have been negative 2 plus 3 would have been 1. So by cleaning this up, remember that anything to the 0 power is 1. So we have x squared times 1. You can actually skip this step if you wanted to, minus 3xy. Which is the same thing as x squared times 1. So x squared minus 3xy. So we're just getting a chance to just kind of play with exponents a little bit here. We're not going too crazy with them. We just want to see what it is we can go back, remember a little bit, kind of play with it a little bit. So why don't you guys do me a favor? Why don't you guys go ahead and take a second there, see if you can't try number 4 and number 5, and then we'll come back and talk about it. So go ahead and pause the video and give it a try. And friends, like I've told you before, I know you never pause the video. I just put it on there because the teacher side of me said, maybe they will this time. Yeah, I know you don't. All right, so x to the negative 1, x minus x to the negative 1. When I look at something like this, this is one where I would have gone ahead and made it be a complex fraction. So x minus 1 over x. Now, in order to get rid of this, I'm going to multiply by that common denominator. So since I see an x, I'm going to multiply everything by x. And friends, if we're multiplying everything on the top and bottom by the same number, what we're really doing is we're just multiplying by 1. And again, like we've said many, many times, math is pretty much just multiplying a whole lot of 1s and adding a lot of 0s together. So the x's cancel out. I'm left with 1 over x squared minus 1. So it looked like it was going to be pretty bad, but honestly, wasn't that bad at all. How about this last one here? All right. Now, remember, if there is no exponent, we assume there is a 1 there. And likewise, if there is no index, we assume it is a 2. So a square root, there's an imaginary 2 there. So what we're really looking at here is we have 4 times. I'm going to change all of these into fractional exponents. So 4 times x to the 1/3 times x to the 2/5 times x to the 1/2. Now, from there, we want to make sure that they all have a common denominator. So 3, 5, and 2. If I'm looking for some number that they all go into, if I wanted to, the easiest way to do it is I just can go ahead and multiply them all together. We're going back to grade school on this one. 3 times 5 times 2, well, that'd be 30. So I can make all these be equivalent fractions so that they're all over 30. So instead of 1/3, I could use 10 over 30ths. All righty. And then instead of 2/5, if I put that over 30, I'd have 12 over 30. And then instead of 1/2, I could make that 15 over 30. And then, friends, once they all have a common denominator, when you're multiplying numbers with the same base, add their exponents. So now I can keep that 30 as a denominator and add 10, 12, and 15. And when I do that, friends, I end up with 37 30ths. So the nice thing about exponents is they also allow us to go ahead and combine radicals that normally wouldn't be able to be combined through multiplication and division. All right, so we're cruising along here. Why don't you guys go ahead and pause the video and maybe try a couple that are just a little bit longer. See what you guys can do with this. All right, go ahead. All right, well, let's see how you did. And again, like I've told you before, if there is no exponent, we assume there's a 1. I'd start off and I would have gone ahead and distribute this 3 into all 3 by multiplying every exponent into it. Notice that 2 to the first still has its exponent multiplied, so 1 times 3. A lot of folks forget to include the constant number when they're distributing that exponent in. -3 times 3 is -9. And then y to the 15. Okay, so I'm going to kind of do 2 steps at once. So I'm going to do the 2 to the 3rd while at the same time go ahead and combining my exponents here. So when I'm dividing numbers with the same base, I'm going to subtract the exponents. So first of all, 2 to the 3rd is 8, 14. Now, I'm going to have my x and I'm going to have my y. So I'm going to go through and I'm going to subtract their exponents. So -9 minus 7. -9 minus 7 is -16. So that'd be x to the -16. 15 minus a -3, that would be 18. So from there, I'm going to go ahead now at this point. Well, let's not use that right there. That didn't quite work out. So I'm going to go ahead and simplify that fraction. 2 goes into both, so I can simplify it that way. And anything that has a negative exponent, I'm going to go ahead and move it down. So that x to the -16, I'm going to move down to the denominator so that it becomes a +16. So all we're doing on these is we're combining our constants numbers. So that way, I don't know why I made that a 2. So that way they are, in least their constant numbers are simplified if we can, and all the exponents are positive. All the exponents are positive, and we essentially, if we can combine them into one variable, we do that. All right, on this next one here, notice I got a -2 again, so it's going to get distributed into everything. I could do that, or if I wanted to, and this is what I'm going to do, I'm going to go ahead and I'm going to flip it right from the very beginning to see if I can't figure that out. While I'm doing that, I'm going to go ahead and combine these exponents and just see if I can't go ahead and make this just a little bit easier for when I get to it. And notice these also have numbers that I can simplify as well. So 8 over 6. So I'm going to do a bunch of things here all at once. So 8 over 6, that's going to become 4 over 3rd. -4 minus 9 would be a -13. And then 9 minus 5 would be y to the 4th. Okay, so those are combined. And now, the reason why I'm not going to distribute that negative quite in yet, I will, but I'm just going to get rid of the negative exponent. If I can get rid of it, let's do that. So that negative exponent means flip a fraction. So since the entire fraction is going to be flipped, I can make all these just go, the denominator become the numerator, and the numerator become the denominator. So I can simplify that just a little bit now. Now, even before I go ahead and put in my 2, I'm going to go ahead and combine everything in that fraction. So on this first fraction, I still have that negative exponent, so I can make that go to the denominator. And I have 3x to the 13th. That almost looked like a 13, didn't it? There we go. And then I see x to the first, I see x to the 10th. So one way to do this, another way to do this is if I know that I have a bigger exponent in the denominator, I can just leave it there and subtract the exponents, putting that x where the bigger one is. So since I know that 10 is bigger than 1, no sense making it a negative just to move it back down later. I can go ahead and just do this. Bigger exponent down here, and then subtract my exponents. Make the 9 come here. All right. So now we distribute our 2 in here. So let's see. We still have this 4y to the 4th. So some of these can become pretty ugly after a little bit, but it is what it is. Again, if we just take it one thing at a time, don't try to do too much, just one thing at a time, you will be totally fine. So we have 9 squared times y to the 10th and x to the 18th. So let's see here, 9 squared, I'm going to go ahead and do a little shortcut here. 9 squared, well, that would be 81. And so now I look at here and I see my 3 and my 81. So I'm going to go ahead and cross cancel. In other words, I'm going to divide this by 3 and I'm going to divide this by 3, just so that way I can kind of just clean this up a little bit and maybe make my simplifying just a tad bit easier. So 3 divided by 3 is 1. So that means that 3 goes away. So I have 4y to the 4th over x to the 13th. And 81 divided by 3 is 27. So 27, y to the 10th, x to the 18th. Now, when we're multiplying numbers with the same base again, you just go ahead and add their exponents. But notice, I still also have these constant numbers that are getting multiplied. Well, I'll just multiply those like normal. So 4 times 27, that is 108. And then y to the 4th, y to the 10th, that'd be y to the 14th. X to the 13th, x to the 18th, that'd be x to the 31. All right, friends. Just about done. We got one quick little application that involves exponents, just so we can kind of get a little bit of work in it. So let's go ahead and clear this out. And let's take a look at that last one. All right, so there is a number that is a constant number. There are 5 constant numbers in math. There's 0, there's 1, there's pi, there's I, and then the last one is the number E. So E is called the Euler number after Leonard Euler, and E is equal to 2.71828182834. So it's the constant number. All right. And that whole idea of the constant number there, it's just one of these random constants. That decimal goes on forever. It's like pi, it just goes on forever. The cool thing about this Leonard Euler guy is he actually was able to figure out that all 5 of these constant numbers relate to each other. No, if you were to plug 1828, it's going to be like pi. We just leave it alone. And you'll even see this on your calculator. You'll see a button on your calculator on the left-hand side. It'll say e to the caret button, so e to the power. So you'll find it on your calculator there. It's on the very left-hand side. Another place where you'll see this number e on your calculator, because you actually can find it 2 different places. The other place you'll find it is on the right-hand side. if you go to and you find the division button on your right hand side, you'll see the number e. So you can, two ways you can make e show up on your calculator. And again, it's like pi, it's just a constant number. So one of the biggest places this Euler number is used is in money or any sort of exponential growth. And the most common formula we have for that is P, which is the principal, the amount of money you're investing, E raised to the RT. Now, if you remember back in integrated 1, you guys had a little formula like this, P1 plus the rate written as a decimal N all over N times T. Now, this was compound inequality. This is where it's compounded periodically. This type of compound is right here, is continuous. It means it goes forever. It never stops compounding itself. So it compounds infinitely. And this is how most money is calculated. So we're going to do a real quick problem here. So P is the starting amount. So if you look at our problem here, here is our P value. $4,729 is invested at a rate. That rate, 2.9, that is your R value. But remember, we have to change that into a decimal. So it's not 2.9, it's going to be 0.029. And T is your time value. So the 13 years, that's your T value. So all we're doing here on these is we're just taking our numbers and we're just plugging them in. So if we plug them into this equation, A equals our P value. So that'd be 4,729. E, the R, which would be 0.029. And the T value, which is 13. So we're just literally going to plug that into our calculator and we're going to press enter. So A would be about 6894. So that means after 13 years at 2.9%, if you were to go through and figure out how much money you would actually have, it would be the 6.429479. So that means the amount of money here, we'll always want to make sure on word problems we write our answer as a complete thought. We'd basically say that the balance, the amount of money you'd have, the balance after 13 years would be, oh, how much is that? 6894.43 cents. And that'd be how much money. So again, don't get too confused when you see this E. E is just a random number. You'll find it on your calculator. All right. Just a random number that you will use. You'll plug it into your calculator. And again, it's called the Euler number. All right. Euler number after the mathematician Leonard Euler. All right. I kind of dig Euler actually a little bit. Cool thing about Leonard Euler, he was a famous French mathematician, but one of my favorite things about these is that he was blind. So much of what he found and discovered, he went blind as a teenager. So much of what he's found and discovered, he had to see in his head. And then he would tell people what's right. And he could see it so clearly that he was able to do a lot of these things. The guy was brilliant. And friends, let that just encourage us. Doesn't matter how we're feeling, whatever disability we may or may not have, we can do anything. You just got to set your mind to it, friends, and you'll be great. So anyways, look forward to seeing you guys in class, and we will I'll be able to have a little more fun then. All right. Take care. Bye-bye.